Hello everyone, welcome to this lecture. So, just to recap, in the last lecture we have introduced digital signatures, we have seen their formal definition. In this lecture we will see an instantiation of digital signatures based on RSA function. Namely, we will first see plain RSA signatures and attacks that can be launched on plain RSA signatures, and then we will see an instantiation of secure signatures based on RSA function, which we call as RSA full domain hash. So, let us start with plain RSA signatures, and for this let me recall the RSA one way trapdoor permutation. We have the parameter, we first generate the parameters n, p, q, where the modulus n is the product of p and q. We pick e and d, where e and d are multiplicative inverse of each other, and then we set the public parameter to be n comma e and the secret parameter to be n comma d, and our forward direction RSA function is x to the power e modulo n, and our reverse function is y to the power d modulo n. And we have proved that both these functions are inverse of each other, and we also consider it to be a candidate one way function where the trapdoor is the d. Now, the plain RSA signature which we can obtain from this RSA one way trapdoor permutation is obtained by visualizing or treating this inverse function as the signing function. That means, any entity who possess n comma d can use the inverse function to compute the signature, and using the forward direction function f to be the verification function. More specifically, the plain RSA signature over the message space Zn star is obtained as follows. The key generation algorithm runs the gen RSA algorithm to obtain the parameters n, e, d, and now the public parameter n comma e is set as the verification key, whereas the trapdoor information, namely n and d, is set as the signing key. To sign a message m belonging to Zn star, we basically compute m to the power d modulo n, where d will be available with the signer, and to verify a message comma signature pair, what we compute first is the value of the RSA function on the signature component, namely we compute sigma to the power e modulo n and compare it with the received message. If the comparison passes, then we accept the message, namely we output 1, otherwise we output 0. So, now we want to analyze the security of this plain RSA signature scheme, and one might say that the following intuitive argument should prove that the plain RSA signature schemes plain RSA signature scheme is indeed unforgeable or secure. So, the argument here is that if I am an adversary and if I do not know the value of the signing key, namely the value of the secret d, and if my goal is to forge a signature on a message m star on which I have not seen the signature in the past, then to forge the signature basically I have to compute the value of m star to the power d modulo n, where I do not know the value of d. And one may argue that this is nothing but an instance of the RSA problem. But since if I assume that my RSA problem is difficult with respect to this gen RSA function, then I can safely claim that this plain RSA signature scheme is secure. But it turns out that this intuitive argument is not correct. One of the reasons is that the RSA assumption of the RSA problem is difficult to solve only if m star is randomly chosen from Zn star. It does not say anything how hard or how easy it is to easy it is to compute m star to the power d modulo n without knowing d for any m belonging to Zn star. The second problem here in this intuitive argument is that the RSA assumption does not tell or does not guarantee anything about an adversary about the possibility of computing m to the power d modulo computing m star raised to power d modulo n, given that adversary might have seen the value of several m to the power d modulo n for any m of its choice. Because remember, when we consider the forgeability game for the signature scheme, adversary is allowed to see signatures of several messages of its choice. So, if adversary has submitted a message m, it would have seen the signature m to the power d modulo n, and it might have seen the value of m to the power d modulo n for polynomial number of messages m. And by seeing the value of polynomial number of values of the form m to the power d modulo n, where m is known to the adversary, the goal of the adversary is to come up with a forgery, namely m star raised to the power d modulo n. So, RSA assumption does not guarantee anything how hard or how easy it is for an adversary to come up with a forgery, given that it has seen the signature, namely the output of the RSA function, for several m of its choice in past. Indeed, it turns out that this plain RSA signatures, there are several, for this plain RSA signatures there are several ways with by which the adversary could come up with a forgery. So, let us see a very simple attack which we call as no message attack. From the name it might look like that there is no message on which the adversary is producing the forgery, but that is not the case. There is indeed a message on which the adversary is producing the forged signature. The reason why it is called no message attack will be clear to you soon. So, the idea behind this attack is that to forge a valid signature, adversary need not always work in the forward direction. What I mean by that is, if we consider the message space and the signature space of this plain RSA signature, both of them are the set Z n star, and the signature for a message m star can be produced by computing m to the power d modulo n. So, if the goal of the adversary is to forge a signature on a message m star, it has to basically compute m to the power d modulo n. That is one of the ways by which adversary can produce a signature, and this I consider to be, this I call as producing signature by walking in the forward direction. But it turns out that adversary could come up or forge a signature by walking in the backward direction as well. Namely, what it can do is, it can first pick up a random signature or a random group element and treat it as a signature, and then it can ask in its mind that what could be the valid or potential message from the message space for which the signature, for which the RSA signature would have been this picked up sigma star. And it is easy to see that by picking a random signature sigma star, the corresponding message m star which would have produced this signature sigma star is nothing but this picked sigma star raised to the power e modulo n. Because if indeed my m star is sigma star raised to the power e modulo n, then this m star comma sigma star constitutes a valid RSA signature as per the RSA verification algorithm. And to compute m star, adversary have everything at its disposal, namely it has sigma star, it knows the value of e and it knows the value of n, and hence it can easily compute m star. So, basically here it is easy to see that by walking in the reverse direction, adversary could come up with a valid forgery even without any access to the signature oracle. It does not ask for the signature of any message of its choice, it just pick a signature and produces a corresponding message. Now, the reason we call this as a no message attack is, here the forgery is produced by walking in the backward direction. The adversary does not have any message to begin with for which it wants to generate a forgery. But still, as per the definition of forgery, the way adversary has computed m star comma sigma star, it is a valid forgery. It is a different discussion whether this m star which adversary has produced by walking in the backward direction indeed makes sense in the context of the application where the underlying signature scheme is used or not. Right. Now, what we are going to do next is, we are going to see a serious attack where the adversary now has a concrete message, and we will see how by using the help of the signature oracle, adversary can come up with a forgery on any message of adversary's choice against this plain RSA signature. Right. So, again to recall, in the no message attack, adversary has no control on the message which it obtains by walking in the backward direction. But a more realistic attack scenario will be where adversary has a concrete message of its choice on which it wants to forge the signer's signature. So, let me demonstrate an instantiation of the attack here. So, as per this experiment, signature forge experiment, the challenger would have thrown the challenge to the adversary, namely the verification key, and say the goal of the adversary is to compute the or forge a signature on a message m star. What it does is, it picks two messages randomly from the set Z n star such that the product of m1 and m2 modulo n is m star. And how it can pick m1 and m2 such that their product is m star? Well, it can first randomly pick m1 from the group Z n star, which requires polynomial amount of time, and then it can set m2 to be the value m star multiplied by multiplicative inverse of m1, that will give him the required m2. which again can be computed in polynomial amount of time. Now, what the adversary can ask is, it can ask for the signature oracle access for the message M1 and M2, namely it asks the challenger to sign the messages M1 and M2. This basically models the fact that in the real world, adversary's goal is to forge a signer's signature on M star. Basically, it is now influencing the signer to sign the messages M1 and M2, right. So, as per the rules of the game, the challenger signs the messages M1 and M2, and now let the adversary combine these two signatures, namely let it multiply the two signatures modulo n, and it submits the forgery M star followed by sigma star. And my claim here is that the probability that the adversary here wins the game is 1. So, sorry for the typo here, this 1 is coming down. So, what I want to say here is that the success probability of the attacker that we have seen here is 1. This is because if you see sigma star, it is nothing but M1 raised to the power d modulo n multiplied by M2 to the power d modulo n, because that is what is the value of sigma 1 and sigma 2. And if we do the mathematics, it turns out that sigma star is nothing but the value of M star raised to the power d modulo n, which is nothing but the RSA signature on the message M star. So, now you have a concrete attack where using the help of the signature oracle, adversary could come up with a signature on any message of its choice, which proves that this plain RSA signature is not secure. So, now the question is, can we design a secure signature scheme based on the RSA function, and the answer is yes. We can construct what we call as RSA full domain hash signature, and on a very high level this might look like an instantiation of the hash and sign paradigm, but actually it is not a full fledged instant implementation or instantiation of hash and sign paradigm. The idea here is we again want to transfer the message bit string which we want to sign before signing using the RSA function. So, what we do is the actual message space which we can sign here or the messages which we can sign could be arbitrary bit string. We map them to the element of Zn star by applying some transformation function which I call as H function, and then the actual transformed message is signed using the RSA signature scheme that we had discussed now, the insecure RSA signature scheme. So, the key generation algorithm for this full domain hash signature is as follows. So, we run the gen RSA algorithm, set sk to be the signing key or n comma d to be the signing key and n comma e to be the verification key, and we make this transformation function h to be publicly known. The transformation function maps arbitrary length bit strings to elements of Zn star. And now to compute a signature on the message M, which is a arbitrary length bit string, what we do is we first compute h of M, that means we map the bit string M to an element of Zn star, and then we compute the value of inverse RSA function on the h of M, namely we compute h of M raised to the power d modulo n, that is our signature. The verification happens in a canonical way, namely if we are receiving a message comma signature and if we want to verify it, what we first do is we compute sigma raised to the power e modulo n and we call it M dash, and we accept the message comma signature only if and only if M dash is equal to h of M, which should be the case if everything has happened in a proper way, right. So, that is the overall idea of this RSA full domain hash. Now, one might wonder that what are the necessary properties that we require from the underlying transformation H to ensure that the overall scheme is secure. I stress here that this full domain hash signature should not be considered as an instantiation of the hash and sign paradigm, because for the security of the hash and sign paradigm we need the fixed length signature scheme to be secure. But the fixed length signature scheme which in this case is the plain RSA signature, we have already proved it is not secure. However, it turns out that we make some suitable assumptions for this underlying transformation function, then this overall way of hashing the message first and then signing as per the insecure or the plain RSA signature gives us an overall secure signature scheme. So, let us discuss what exactly are the security properties that we require from the transformation function. So, the list of the necessary properties is as follows. Definitely we require that the transformation function should be collision resistant, namely it should be computationally difficult for a polytime adversary or an attacker to find out a pair of messages m and m dash such that the transformed m and the transformed m dash are same, because if that is the case, that means if the adversary could come up with such a pair of m and m dash, then it can first ask for the signature on the message m, and the signature on the message m dash will be exactly the same as the signature on the message m. So, it could easily come up with a forgery. The second requirement from the transformation function is that it should avoid any kind of multiplicative or nice algebraic properties, which we had exploited in the attack on the plain RSA signature. That means, it should not happen that we should have a triplet of the form m, m1, m2 such that the transformation of m is equal to the product of the transformation of m1 and the transformation of m2, because if it is possible for an adversary to find out such triplets in polynomial amount of time, then what adversary basically can do is it can ask for the signature on the message m1 as per this full domain hash, it can ask for the signature oracle access for the message m2 as per this full domain hash, and given that it can easily obtain a signature on the message m, that could be its forgery. So, we would like that this transformation should be such that it should has no such nice algebraic properties. We also need the one-wayness property from this transformation property transformation function, namely we require that it should be given an arbitrary x from z n star, it should be difficult to find a message m such that h of m is equal to x. This is to prevent the no message kind of attack, right, because if this one-wayness property is not satisfied, namely if it is easy for an adversary to compute such an x and m such that h of m is equal to x, then again the adversary can launch the attack that we had seen in the no message attack. However, it turns out that definitely these three properties are required, but we do not know whether the list is exhaustive or not, whether we need any fourth property, fifth property and so on, right. So, we are kind of stuck now. So, what we can do is we do not care about whether the list is exhaustive or not. If we assume that the transformation function is modeled as a random oracle, and if we are in the random oracle model, then we can give a complete security proof for this full domain hash signature. So, you can see that if we assume that if we are in the random oracle model, then definitely the three requirements that we have stated will be satisfied. And top of that, the proof that this signature scheme is secure in the random oracle model takes care of the fact that no other attack can be launched, this no kind of attack can be launched against this RSA full domain hash signature, and the list of properties that we are going to obtain by assuming that my transformation function is in the random oracle model will be exhaustive. So, I am not going into the full details of the full formal details of the proof that indeed this signature scheme is secure in the random oracle model. If you are interested to see the full formal proof, you can refer to the book by Kartzlinder or by the manuscript by Bonnet and Shu. So, that brings me to the end of this lecture. Just to summarize, in this lecture we have seen an instantiation of secure signature schemes based on RSA functions. We had first seen the plain RSA signatures, and we have proved that it is not secure by demonstrating two possible attacks, and we have seen an instantiation of secure signature schemes based on RSA function in the random oracle model. Thank you.